Let's consider that you have a highly reflective surface. Highly reflective meaning that it's a smooth surface with no impurities on it. Moreover, let's suppose that you have 3 incident rays of light that are incident on that reflective surface. In that case, these incident rays of light, when they reach that reflective surface, they are going to bounce off in a different direction, as we can see in that figure. And the phenomenon occurring in that case is going to be called the reflection of light. In addition, if you have a look at these reflected rays of light, they remain parallel to each other even after reflection, and therefore such reflection is denoted as a specular reflection. So what's a specular reflection? A specular reflection, it's a reflection that occurs off of smooth surfaces, such as mirror-like surfaces, where the reflected rays of light, they would preserve the same outgoing direction, meaning that they would remain parallel to each other even after reflection. Now at each point of incidence over here, if we construct the normal, so at the first point of incidence, if we construct the first normal, then the second normal at the second point of incidence, and the third normal at the third point of incidence. In that case, we can distinguish 2 different angles. We can distinguish an angle of incidence and we can distinguish an angle of reflection, where the angle of incidence would be the one which is formed between the incident ray of light and the normal, and the angle of reflection is going to be the one which is formed between the normal and the reflected ray of light. Therefore, the law of reflection for a specular reflection would state that the angle of incidence is equal to the angle of reflection. So in that case, theta r or theta I is equal to theta r for a specular reflection. And in a similar manner for the second ray, we can also distinguish another angle of incidence and another angle of reflection, and the same thing for the third incident ray and the third reflected ray. So for all of these rays, if you bring a protractor and you measure the angle of incidence and the angle of reflection, you are going to validate that the angle of incidence is equal to the angle of reflection, and that would be in the case of a specular reflection where you have a mirror-like surface. And such statement that the angle of incidence is equal to the angle of reflection is actually a special case of Snell's law. So Snell's law, it yields that an I sine theta I is equal to an R times sine theta R. So in our case, both rays of light, the incoming and the outgoing ones, they are both occurring in the same medium. Therefore, we have the same index of refraction at both sides. Therefore, an I and an R, they can be eliminated. Therefore, we have sine theta I equal to sine theta R. Therefore, theta I is equal to theta R. And therefore, we have that the angle of incidence is equal to the angle of reflection in the case of a specular reflection. Now, the opposite of the specular reflection would be the diffuse reflection, where the reflection of light would occur off of a rough surface. So in that case, as you can see in the figure below, the reflected rays of light, they are directed in random and different directions. However, in our case today, we are going to limit our study to the case of the specular reflection, since it is actually the easiest case to study. Now, the diffuse reflection, it would come in handy if you are in the field of material science and optics. In that case, if you are studying, let's say, the thermal properties or the optical properties of certain materials at the nanoscale level, the majority of times such reflections within such materials, they are going to be more diffuse than specular. So in that case, the specular reflection would serve as a fingerprint for that material in order to study its optical and thermal properties. Let's suppose that you have 2 different transparent mediums. You have free space medium and glass medium, and each one, of course, it has its own index of refraction. And then you have a ray of light which is traveling through free space and being incident on that interfacial boundary that is separating free space from glass. At the point of incidence over here, you can start by constructing the normal. So since light is traveling from a rarer region to a denser region, meaning from a region of low index of refraction to a region of high index of refraction, therefore, upon entrance of that incident ray of light into that second medium, light would undergo bending. In other words, refraction occurs. So what is refraction? Refraction is simply the change of direction that light would undergo when it enters into a different transparent medium that has a different index of refraction from the one in which light was propagating originally. So in that case, since that incident ray of light is propagating from a rarer region into a denser region, therefore the propagating ray of light into that denser region is going to be bent, or it's going to be refracted toward the normal, meaning it's going to approach the normal. So over here, that refracted ray of light is going to be refracted toward the normal by approaching that normal. Therefore, Snell's law would yield in that case, so Snell's law would yield that Ni times sine theta I, meaning that the index of refraction of the first medium in which light is propagating times sine of the angle of incidence, which is the angle formed between the incident ray of light and the normal, is equal to Nr, which is the index of refraction of that second transparent medium in which light has emerged, times sine theta r, where theta r would be none other but the angle of refraction. So over here you have to distinguish between theta r, which has been defined previously as the angle of reflection, and theta r over here, which is none other but the angle of refraction. So theta r in that case would be the angle formed between that propagating ray of light and that second medium and the normal. Now the question is, what's actually causing the refraction of light in that second medium? Why did light undergo bending in that second medium? When light is moving through vacuum or free space, light has a certain speed, which is none other but the speed of light that is given theoretically to be c equal to 3 times 10 to the power 8 meters per second, and that would be in vacuum or free space. So what would be the speed of light in any other medium that is different than vacuum? So if you have light traveling in any other medium which is not vacuum, what would be the speed of light in that case? Light has a dual nature. It has a wave nature and it has a particle nature, meaning that light can behave as a wave and it can behave as a particle, where the particle nature of light is actually attributed to photons, which are energy packets that consist the essence of light. So upon entrance of light in that glass medium, these photons, they are going to collide with the atoms or the molecules that make up the solid structure of that glass medium. So upon collision between the photons and the photon's energy is going to be absorbed by these atoms. However, these atoms, they are going to instantaneously release that absorbed energy, and they are going to release it in the form of a photon of light. So that delay in time that exists between the absorption of energy and re-emission of that energy is what causes the apparent slowing down of the speed of light in that second medium. So over here we have that incident ray of light which is moving from free space into glass. So upon entrance of that ray of light into that second medium, the photons which are carrying energy, they are going to collide with the molecules of that glass medium. So upon collision between the photons and the atoms are going to absorb upon collision some of the energy of that photon. However, instantaneously these atoms are going to release that absorbed energy, and they are going to release it in the form of a photon of light. So over here we have two processes. We have the process of absorption and then we have the process of emission. So that delay that exists between the absorption and the re-emission is what causes the apparent slowing down of the speed of light in that second medium, and therefore causing light to undergo bending in that second medium. So now we are going to study the inverse case to the one that we have studied before. So now you have the incident ray of light which is moving from glass to air. It's moving from a denser region into a rarer region. So over here we have a glass region and over here we have a free space medium. So we have the incident ray of light now moving from a denser region into a rarer region, and as we have seen before, whenever light is moving from one medium into another transparent medium, light is going to undergo bending in that second medium. So over here, upon emergence of that incident ray of light into that second medium, which is free space, it's going to undergo bending. However, since we are moving from a denser region into a rarer region, therefore that emerging ray of light is going to be refracted away from the normal. So that emerging ray of light over here, it's going to be bent away from the normal. So in that case, if we keep incrementing the angle of incidence, or the angle at which that incident ray of light is being incident on that interfacial boundary separating glass from free space, over here that propagating ray of light or the emerging ray of light is going to keep being refracted further away from the normal until we reach a certain point where, for a certain angle of incidence, the refracted ray is going to make an angle of 90 degrees with that normal. So if we keep incrementing the angle of incidence, we are going to reach a certain angle of incidence over here for which the angle of refraction is going to be 90 degrees, meaning that the refracted ray is going to make an angle of 90 degrees with that normal. And such angle of incidence is going to be referred to as the critical angle. So the critical angle is simply a very specific angle of incidence for which the angle of refraction is going to be 90 degrees, meaning that now that refracted ray of light is going to be making an angle of 90 degrees with that normal. Therefore, Snell's law would yield that an I times sine theta I is equal to an R times sine theta R. So in the case of the critical angle, we are going to replace theta I by theta C. So now we have an I times sine theta C equal to an R, which is none other but the index of refraction of that second medium, which is free space. So it's 1 times sine theta R, which is none other but 90 degrees, which is also 1. So sine 90 is 1. Therefore, we have that sine theta critical is equal to 1 over an I. Therefore, theta critical is equal to sine inverse of 1 over an I. Now, what would happen if we exceed that critical angle? So over here we have reached a certain angle which we have referred to as theta critical. Now, what would happen if we exceed that critical angle? So we have reached the critical angle for which the angle of refraction is equal to 90 degrees. Now, what would happen if we go beyond theta critical? If we go beyond theta critical, therefore now we have a total internal reflection. So that refracted ray is going to turn into a reflected ray, and therefore we have the law of reflection all over again. So for any angle theta prime which is greater than theta critical, therefore we have a total internal reflection, meaning that over here that a refracted ray is going to turn into a reflected ray, and therefore we have the law of reflection all over again, for which the angle of incidence is equal to the angle of reflection. Moving on to the case of the dispersion of light. So what do we understand by the dispersion of white light? Dispersion is basically the splitting up or the separation of white light into its main constituent colors, which ranges from extreme red until extreme violet. If we look at the following figure over here, we have a ray of white light which is incident on an inclined plane of a glass prism. So when that incident ray of light emerges or propagates into the glass prism medium, from one side we are going to have a refraction of light, and from the other side that white light is going to be divided or split up into its main constituent colors, which ranges from extreme red until extreme violet. But what is actually causing the dispersion or the splitting up of white light into that glass prism medium? Since white light consists of many colors of light, therefore each color of light is going to have its own wavelength, and each wavelength is going to have its own velocity. So we have seen before that when light is traveling from one transparent medium into a different transparent medium, the velocity of light is going to apparently change in that second transparent medium. And the same thing for the colors of light. Since each color of light has its own wavelength, therefore that color of light is going to have its own speed of propagation in that transparent medium. So the red light is going to have its own velocity, the blue, the yellow, the green, etc. Moreover, the wavelength and the speed of light, they are related by the equation V equal to lambda f, where V in that case would be the speed of light and the medium where that color of light is propagating. So V is going to be the speed of light, or the speed of color of light in the medium. Lambda is going to be none other but the wavelength of the color of light. And then over here we have f, which is none other but the frequency of that color of light. So as we can see, whenever the wavelength of each color of light varies from green to blue to yellow to violet to red, etc., therefore the corresponding speed of the color of light and the medium where that light is propagating is going to vary as well. So each wavelength has its own velocity. Furthermore, the index of refraction is actually related to the speed of light by the following equation: n equal to c over v, where c in that case would be the speed of light in vacuum, and v would be none other but the speed of that color of light in the medium where that light is propagating, and n would be the index of refraction. So in that case, since each color of light has its own speed in the medium where it's propagating, therefore each color of light is going to have its own index of refraction. So the index of refraction is going to vary from one color of light to another. So the red, the green, the blue, the yellow, the violet, etc., they are all going to have their own separate indices of refraction. So for that matter, when a white light enters into a prism, as we have seen before, white light is going to be split up, or it's going to be separated into its main constituent colors, and this is because each color of light has its own index of refraction. So the index of refraction, it's an indication of the refraction of light within a certain medium. So since each color of light has its own index of refraction, therefore we are going to observe the splitting up of white light into its main constituent colors, and therefore forming a spectrum, which is another about the spectrum of white light, which consists of colors that ranges from extreme red until extreme violet. So the main idea over here that since each color of light has its own index of refraction, therefore each color of light which consists of white light is going to be refracted at a slightly different angle in comparison to the other colors of light. There is still one more idea that I want to discuss, which is the difference between the reflection and the refraction of different colors of light. What would be the difference in that case? So let's suppose over here that you have three parallel rays of light of three different colors. You have red, blue, and green rays of light that are incident on that highly reflective surface. In that case, in what order do you think the reflected rays of light are going to be reflected? Are they going to preserve the same order of red, blue, green, or are they going to switch orders depending on their index of refraction? Since in that case over here we have a purely reflection phenomenon occurring, and that reflection phenomenon is basically occurring in free space. So over here, these three rays of colors, they are actually propagating in free space, and the reflection is also going to occur in free space. Therefore we don't have any refraction of light occurring. Therefore, the index of refraction of each light is not going to play any role in the order in which these rays of light they are going to be reflected. In other words, they are going to preserve the same order of reflection. So first off, you are going to have the red color being reflected, followed by the blue color, followed by the green ray of light. So as we can see, the reflected rays of light, they have preserved the same order of colors simply because the reflection and the incident rays of light, they are both present in the same medium, which is the free space medium. Therefore, the index of refraction is not going to play any role in that case in the order in which these rays of light they are going to be reflected. Whereas if you had a prism, let's say over here you have a prism instead, and you have the red color of light being incident on that prism, followed by the blue ray of light, and followed by the green. In that case, the refracted rays of light or the transmitted rays of light from that second surface, they are not going to preserve the same order. They are not going to preserve the same order of colors, meaning that you're not going to have the red light followed by the blue followed by the green, but instead, depending on each index of refraction of each color, you are going to have a particular color being refracted first, followed by another color, followed by the third color. So it's not necessarily the case that the refracted rays of light or the transmitted rays of light are going to preserve the same order of colors. And in addition, since each color of light is being refracted at a different angle, therefore the transmitted rays of light, they are not going to remain parallel to each other even after transmission.